Okay, next let's look at your free body diagrams. So first thing is just kind of in your own words. You want to say what's the point of a free body diagram? What does it show? Why is it useful to show it? And what I threw up there is just kind of, it helps you isolate the forces that are acting against your object in any given direction. So one part of the system, is it something that's pushing it right, pulling it left, dragging it down, lifting it up? It just helps you isolate, okay, what are all the forces acting on here? And it kind of simplifies, you have a big long word problem, but if you can put it into a box with a couple arrows, it should make everything much easier and much simpler. So let's look through our 6 free body diagrams. Number 1, it says a book is being pushed across the table to the right. So to start, let's put our book here, and it's going to be getting pushed to the right. So if it's being pushed to the right, remember we just said in the last one, anytime there's a push or a pull, then we know that, anytime one thing is pushing on another, it's force normal. And we also know that it's moving to the right. So if we're pushing against the table, there's definitely going to be some friction because there are 2 objects rubbing on each other. So there's going to be the force friction, but it'll be smaller because we know it's moving to the right. So the force that it's being pushed with is greater than the force that is resisting it. So it's greater than that force normal. All right, pulling down, we can just assume this is happening on Earth, is going to be gravity, and pushing back up from the table with the same force that is being pulled down by gravity is force normal. So for this very first one, we have 4 different forces acting on it. Force normal, gravity, and friction. All right, next up, a duck is floating in water. Once again, I'm going to draw my duck here, see what you think of it. It's a pretty good duck. I'm guessing that we're on Earth here, so we can put in force gravity right away. But it clearly says it's floating. The duck isn't sinking in the water. So it has an equal force pushing back up on it, and because it's the water pushing up on the duck, well then it is force normal. The word question says nothing about movement right to left, so we're good. All right, next up, a light bulb hanging from a wire on a ceiling. This one I'm going to move up to the side so not in the light. So first thing I want to do is draw our light bulb. There we go. Once again, it's on Earth. So we're going to put gravity in. But it's not falling down. What is it holding up? Well, it's hanging. So as soon as we see hanging, we know that it's on a rope, a string, a wire, something like that. So then we have equal force of force tension. Remember, if there's no movement, these 2 arrows have to be equal. Although I drew my bottom one a little darker, they're the same size. The only time we make it so one arrow is bigger than the other is if there is movement. Like here it says the book is being pushed across to the right. If we scroll down, we have questions 4, 5, and 6. So question 4 wants you to draw a free body diagram for you sitting in a chair. So let me look at you really good. All right, let me get this just right. Yeah, that looks good. That looks a lot like you. You are sitting in a chair on Earth. So, of course, we have gravity pulling us down. And then the chair is pushing back up against you, keeping you from falling to the ground. So since it's one pushing on another, we have force normal. There's no left-right movement up here, so there's nothing we can put on either side. Number 5, a sled being pulled to the left by a rope. So we're going to draw our sled in here, and we know it is moving left. So I'm going to put a nice big arrow there, and it's being pulled by a rope. So remember, anytime there's a force that's being applied by a rope, a string, something like that, it becomes force of tension. If the sled is being pulled across the ground, there's definitely going to be the sled rubbing against the ground that it's being pulled on, but we know it's moving, so this arrow is going to be smaller force of friction because the force tension is greater than the force of friction, which is why there's movement. Unbalanced forces, that's movement, right? And we can assume this is on Earth, so of course we would have force gravity, but the ground pushing back up against the sled is equal force normal. So you pretty much always are going to have a force gravity, as long as it doesn't say it's in outer space, force gravity down, and some other force pushing back up, and then you just have to figure out, all right, am I moving it right or left in this example? All right, in the final free body diagram, this is an open parachute falling to the ground. So we're going to draw our box first, and now we have, it says falling to the ground, so we know there's downward movement. If it's going towards the ground, we know it's gravity pulling it down. But if it's a parachute, it's falling to the ground much slower than it would be, obviously, without a parachute. It's kind of the point of the parachute. So we're going to put a smaller force, smaller arrow, and this would be force of drag. It's air resistance holding that person up, or holding you up. All right, so these are questions 4, 5, and 6 for free body diagram.